Welcome, curious listeners, to The Deep Dive, the show that cuts through the noise and extracts the most important nuggets of knowledge from the information you need to master. Today, we're diving into something truly pervasive, something that powers our entire modern world, yet often goes completely unnoticed: electricity. It hums through our walls, charges our devices, lights our homes, and keeps our industries running. It's an invisible force, immensely powerful, and, well, if mishandled, incredibly dangerous. We rely on it every second, often without a second thought. So what is this complex, invisible shield that keeps us safe from such a potent, unseen energy? How do we live so safely alongside something so powerful? Okay, let's unpack this.
That's the perfect question to kick things off. Our deep dive today focuses on that very shield, the Electricity Safety Regulations 2010, officially known as SR 271036. Now, this isn't just some dense legal text. It's the meticulously crafted, comprehensive framework that governs pretty much every aspect of electrical safety in New Zealand. Think of it as the unseen blueprint and ongoing guardian protecting every home, every office, every public space, every piece of equipment where electricity flows. For you, the listener, these regulations are the invisible backbone ensuring that when you flip a switch, the lights come on, not, a disaster. Our mission with this deep dive is really to extract the core insights from these regulations, offering you a shortcut to understanding how electrical safety is managed with such precision. It's a robust, living system constantly updated, and for this session, we're drawing from the 2019 reprinted version, which highlights its enduring relevance and adaptability in a world that's constantly, innovating with electricity.
Right. So to truly understand this invisible shield, we need to begin with the most fundamental question. How do the regulations actually define safety? It can't just be a vague idea, can it? When we talk about electrically safe in the eyes of these regulations, what exactly does that mean?
You've hit on a key point there. Regulation 5 provides a really profound definition, actually. It states that electrical works, installations, fittings, and appliances are electrically safe if there's no significant risk that a person or property will be injured or damaged by dangers arising directly or indirectly from the use of or passage of electricity through them. Conversely, something is electrically unsafe if there is a significant risk that a person may suffer serious harm or that property may suffer significant damage.
That significant risk threshold seems incredibly critical. What's the real implication of phrasing it that way? It sounds like it gives us some flexibility, maybe.
What's fascinating here is how this definition lays the groundwork for absolutely all subsequent rules. It's not just legalese, it's a profound regulatory shift. Instead of simply asking, did you tick boxes A, B, and C, it fundamentally asks, is the end result genuinely safe, even if an unforeseen hazard emerges? This empowers regulators to adapt to new technologies and unforeseen risks, ensuring the spirit of safety is always upheld, not just the rigid letter of a fixed rule. That's a truly dynamic safety principle.
Okay, I see. So it's outcome-focused, really.
Exactly. For you, this means that the design of your home appliances, the wiring in your office building, or even the power tools you use are all constantly striving to meet this electrically safe threshold. It's an ongoing commitment to preventing harm, not just reacting to it after an incident.
That makes perfect sense. So with that broad understanding of what safe actually means, what kind of electrical work are these regulations really concerned with? Does it apply to absolutely everything, or are there specific high-stakes activities it targets? What exactly defines prescribed electrical work?
You're right, not all electrical work carries the same level of risk, and therefore not all of it falls under the same rigorous oversight. Regulation 6, in conjunction with Schedule 1, clearly distinguishes what is and what is not prescribed electrical work. And this is absolutely crucial for understanding who is qualified to do what and where the most stringent safety rules apply.
Okay, let's dig into that distinction then. What is considered prescribed electrical work according to Schedule 1, Clause 1? Give us some examples of the kind of work that truly demands a professional electrician's touch and, high levels of regulation.
Right. Clause 1 outlines quite a range of activities deemed high risk. It includes fundamental tasks like connecting new electrical installations to the power supply or extending existing electrical circuits within a building. Pretty standard stuff for an electrician. It also covers inspecting high-risk electrical work, ensuring an independent check is performed, so quality control is built in. Then there's specialized work, such as modifications to mining electrical equipment, which, as you can imagine, carries unique hazards. Crucially, it extends to installing specific types of fittings and appliances, for example, medical devices in patient treatment areas, or any electrical equipment in hazardous locations, like where flammable gases might be present, very sensitive areas. And here's the layered accountability. The certification, inspection, and supervision of all this high-risk work are themselves considered prescribed electrical work.
Ah, so even checking the work is prescribed work.
Exactly. It means every step from initial setup to final sign-off is subject to the highest safety standards, designed to capture any activity that carries inherent significant risk, requiring professional competence and oversight.
Now, here's where it gets particularly interesting for the average person. What about the things that are not considered prescribed electrical work, as outlined in Schedule 1, Clause 2? There are some surprising exclusions here that most people wouldn't expect. I mean, can I really mess with my home's electricity without bringing in a pro? Sometimes.
You might be surprised. Clause 2 carves out several important exceptions. For instance, replacing a fuse link with one of an appropriate rating is not prescribed work, provided it's done according to the Electrical Code of Practice, ECP 51.
ECP 51. What's that exactly?
Think of ECP 51 as the industry's official how-to guide for common low-risk electrical tasks. It means if you're just changing a standard fuse and you follow this specific approved procedure, it's considered safe enough not to need a professional electrician. Similarly, work on extra low voltage systems, that's typically anything under 50 volts AC or 120 volts ripple-free DC, is generally excluded as long as it's not in hazardous areas or medical locations.
So if I'm just replacing a light switch, or maybe a power outlet, as long as I'm not fundamentally rewiring anything and I've definitely turned off the power at the switchboard, I might not be performing prescribed electrical work.
Precisely. Other exclusions include simply operating works, installations, or appliances like loading, removing, or replacing those fuse links we mentioned. Even certain routine maintenance on domestic appliances, if done strictly according to the manufacturer's user instructions, isn't prescribed. And this is the surprising part you mentioned. Experimental work on radio or electronic apparatus, like tinkering with hobby electronics, is typically excluded. Also, work on telecommunications lines is generally excluded, where shock currents remain well within safe, internationally recognized IEC standards.
So tinkering with my Arduino board isn't going to get me into trouble with these regulations?
Generally, no. These exclusions are very deliberate. They're designed to allow minor, low-risk activities to be performed by competent individuals without triggering the full regulatory burden while still maintaining overall safety. The key differentiator is the level of inherent risk and the potential for exposure to high voltages.
That raises an important question. Why is it so vital to differentiate between prescribed and other electrical work? Doesn't it just add complexity to what seems like it should be a straightforward safety code?
Not at all. Actually, it's about smart, efficient safety management. This tiered approach contributes significantly to overall safety by focusing expert attention and the most stringent regulations where they're most needed. By clearly defining prescribed electrical work, the regulations ensure that only appropriately qualified and authorized individuals undertake high-risk tasks. This prevents untrained individuals from, inadvertently creating serious hazards. For other lower-risk activities, it allows for more flexibility without compromising the fundamental principle of electrical safety. It's about efficient allocation of regulatory oversight and ensuring that the right skills are applied to the right jobs.
Right, matching the level of oversight to the level of risk.
Exactly. It also streamlines enforcement, allowing WorkSafe, the primary regulatory body, to concentrate resources on activities with the highest potential for harm, leading to a safer electrical environment for everyone.
Before we move on, let's briefly touch upon a few other crucial definitions from Regulation 4 that help provide context for this whole framework. We hear terms like AC and low voltage thrown around. But what do they truly mean in this context? Because they sound simple, but I bet they have very specific legal definitions here.
Absolutely. Clarity on these terms is vital to understanding the scope. AC simply stands for alternating current, which is the most common form of electricity supplied to homes and businesses globally. Pretty straightforward. Low voltage, however, is defined differently depending on the context, which is important. For mining electrical equipment, it means exceeding 50 volts AC or 120 volts ripple-free DC, but not exceeding 1200 volts AC or 1500 volts ripple-free DC.
Okay, so a higher threshold for mining.
Yes. In all other cases, it's any voltage exceeding 50 volts AC or 120 volts ripple-free DC, but not exceeding 1000 volts AC or 1500 volts ripple-free DC. This distinction really highlights the uniquely hazardous environment of mining operations, where higher voltages might still be considered low voltage relative to the immense power involved, but still require specific, very stringent controls.
That's a significant difference. And what about MN system? That sounds quite technical. MEN.
MNN system stands for Multiple Earth Neutral System. It's a New Zealand variant of the internationally defined TNC system of electricity supply. In simple terms, it's where the neutral conductor, which carries the return current, is connected to Earth not just at the main power source like a generating station or substation, but also at various specific points throughout the distribution network, for instance, at a main switchboard in a building.
So multiple earth points for the neutral wire.
That's the core idea. You can think of a MN system as a comprehensive, robust grounding system, like the grounding of a house, but scaled up for an entire network. It provides a critical safety path for fault currents, quickly diverting dangerous electricity to Earth and triggering protective devices like circuit breakers or fuses. This prevents dangerous voltages from building up on exposed conductive parts during a fault, effectively protecting people from electric shock and property from damage. It's a foundational safety feature, really fundamental to how our system works here.
So it's about incredibly robust grounding and fault protection. Makes sense. And connectable installation and medical location. Those sound like areas with very specific risks.
They are indeed. Connectable installation refers to mobile structures like caravans, relocatable buildings, or pleasure vessels that are designed to connect to an external power supply. These typically operate at standard low voltage, between 90 and 250 volts AC. This definition ensures that even mobile or temporary structures adhere to the same rigorous safety standards as fixed buildings when they plug into the grid.
Like ensuring your caravan's wiring is safe before you plug it into the campsite.
Exactly. Medical location is a patient treatment area or any other place specifically designated for patient treatment. These definitions are crucial because they trigger specialized, often much stricter, safety requirements due to the increased vulnerability of individuals receiving medical care or the unique nature of the electrical equipment used in these settings.
Right. With all those fundamental definitions firmly in place, now we can really delve into the core of these regulations. Who actually carries the weight of responsibility for electrical safety? It's far more than just the person doing the wiring, isn't it? It extends all the way to the property owner and even the person just plugging something in. Here's where it gets really interesting because it affects almost everyone.
It absolutely does. The regulations lay out clear duties across a broad spectrum of individuals and entities. First, and perhaps most importantly, Regulation 13 covers doing the work safely. Any person who carries out electrical work, whether on new installations, existing fittings, or appliances, has a primary duty to ensure that the resulting work is electrically safe. Furthermore, if you're working on just a part of an existing system, you must ensure your work hasn't adversely affected the safety of the rest of the installation. You can't make things worse elsewhere.
That seems fair. Don't break something else while fixing one thing.
Precisely. And, critically, while you're actually doing the work, you must take all reasonably practicable steps to protect both people and property from dangers arising from that work. This means active hazard identification and mitigation throughout the entire process, not just checking the end result.
So it's not just about the final outcome, but the safety of the process itself. Makes sense. What about reliance on manufacturer instructions? Can an electrician just assume those are safe to follow?
That's precisely what Regulation 14A, Manufacturer's Instructions, addresses. If a manufacturer or importer supplies a fitting or appliance with instructions for use in New Zealand, those instructions must be such that, if followed, the resulting product will comply with the regulations and be electrically safe. What's vital for the person doing the work is that they are entitled to rely in good faith on these instructions as complying with the safety requirements.
In good faith.
Uh-huh.
So unless something looks obviously wrong.
Exactly. This creates a critical chain of responsibility, ensuring that fundamental safety is built in from the design stage and that workers can trust the information provided to them unless they have clear reason not to.
That's a good safeguard, but it sounds like the buck could stop with a lot of different people. What about the person who just uses the electricity or owns the equipment without doing any work themselves? Like if my old toaster starts sparking, am I responsible?
That's where Regulation 15, using safe equipment, comes in, and it has a very strong prohibition. An owner or operator, or even someone who directly rents, hires, or leases electrical works, installations, fittings, or appliances must not use or allow any other person to use that equipment if it is electrically unsafe. And the regulations mean business here. If you use or allow someone to use unsafe equipment, knowing or being reckless as to whether it's unsafe, you commit an offense liable to a Level 2 penalty.
Wow, level 2 penalty. That sounds serious.
It is. This highlights the broad reach of these regulations. It's not just about electricians and installers, but about everyone who owns, operates, or even rents electrical equipment. The onus is on users to ensure the safety of what they're using, emphasizing continuous vigilance.
Wow, so if my old sparking toaster is definitely unsafe, I can't just keep using it until I get a new one. That puts the responsibility directly on the consumer, or the owner anyway. And what about landlords? Do they have specific obligations to ensure the safety of electrical fittings for their tenants? Seems like they should.
They absolutely do under Regulation 16, landlord obligations. Landlords of residential premises have specific enforceable responsibilities. They must not provide or allow the use of electrically unsafe fittings or appliances within their rented properties. Furthermore, they're legally required to provide adequate instructions to the occupier for the safe use of any fittings or appliances supplied as part of the tenancy.
So they can't just dump an old fridge in there without telling the tenant how to use it safely if there are any quirks.
Right. And again, a level 2 penalty applies if a landlord knowingly or recklessly provides or allows the use of unsafe equipment. This underscores the comprehensive nature of the regulations, extending safety responsibilities directly into the rental housing market. It's about protecting the most vulnerable users by placing clear duties on those providing the equipment, recognizing that tenants may not have the expertise or ability to assess electrical safety themselves.
It's clear that these regulations aim to cover every conceivable point of contact with electricity. What about immediate danger? Are there rules for when something goes terribly wrong or seems about to?
Yes, immediate action and communication are critical. Regulation 19, notifying WorkSafe of danger, imposes a duty on anyone carrying out electrical work or assessments to notify WorkSafe if they encounter immediate danger to life or significant property damage. This ensures that serious hazards are brought to the attention of the regulatory body quickly, allowing for rapid intervention if needed.
And what about warning others? We often see signs around construction sites or where repairs are happening, like those danger electricians working signs. Is that regulated or just good practice?
It's absolutely regulated. Regulation 18A, signs when carrying out prescribed electrical work, requires a person carrying out prescribed electrical work to erect or affix warning signs at each access point to the area where the work is being done if there's a reasonable risk of injury from electric shock.
Okay, so it's mandatory if there's a risk.
Yes. Imagine a bustling construction site, or perhaps an old building undergoing renovation where wiring is exposed. These signs are a direct result of this regulation, ensuring that anyone approaching the area is made aware of the potential danger. It's a proactive, visible measure to protect the public and other workers who might not be directly involved in the electrical work, serving as a constant reminder of the unseen hazards.
So far, we've talked about what safe means and who's responsible. But the regulations go further than just saying, be safe. They define specific conditions under which something is deemed to be electrically unsafe. This is about proactive prevention, isn't it? It removes ambiguity and provides clear benchmarks. Takes the guesswork out.
Precisely. These deeming provisions are incredibly important because they set clear, objective benchmarks for what constitutes an unacceptable risk. It means you don't have to wait for an accident to prove something is unsafe. If it meets these criteria, it's already considered a hazard, and immediate action is required. It's a preventative approach that leaves very little to subjective interpretation.
Give us some examples of these deemed unsafe conditions. Starting with works and installations, what kinds of structural or functional flaws automatically make something unsafe?
Right. Regulation 20, electrically unsafe works and installations, is quite detailed, highlighting multiple layers of protection. Works and installations are deemed unsafe if they lack fundamental measures to prevent accidental contact with exposed live parts. That's a basic one. They're also unsafe if they don't provide for automatic power supply interruption, meaning the power doesn't immediately cut off upon a fault that could cause injury or damage. Think circuit breakers or RCDs not working. A very technical but life-critical point is the failure to prevent or limit electric shock currents to within internationally accepted IEC shock current standards. This refers to specific safety curves, like C1C2 of Fig 20 of IECTS 60479-1 for high-voltage systems.
That might sound like jargon, but it's about life and death, right? Can you explain that a little more simply? What are those IEC standards really getting at?
Absolutely. These standards, like IECTS 60479-1, aren't just arbitrary numbers. They're based on extensive research into how much electricity for how long a human body can safely withstand. They literally define the line between a minor jolt and a potentially fatal shock, ensuring that protective systems cut power before reaching that critical threshold. So it's about physical protection, automatic shutdown, and rigorously controlling shock currents to within scientifically determined safe limits.
Okay, that makes it clear. What else falls under this deemed unsafe for installations? Seems like a long list.
It continues, yes. If fittings don't match the characteristics for their intended use, or if they are insecurely mounted or have impaired cooling, they're deemed unsafe. This can lead to overheating and fire risks, obviously. Fittings that cause or are subject to high temperatures or electric arcs and are placed or unguarded in a way that creates a risk of ignition or injury are also unsafe. A very specific point is the improper substitution of refrigerants in electrical equipment with those of higher toxicity or flammability, which is a major fire and health hazard. You can't just swap refrigerants without checking compatibility and safety.
Wow, even refrigerant choice is covered.
Yes. Furthermore, if cables are bent beyond their design criteria, that damages the insulation and conductors, or if there's insufficient space, access, or lighting for safe operation, maintenance, repair, testing, and inspection of fittings, excluding cables and buried earthing, the entire system can be deemed unsafe. This comprehensive list ensures a high level of scrutiny for overall system integrity, covering everything from design to physical accessibility. It's thorough.
Wow, that's incredibly specific. It leaves very little to chance. What about individual fittings and appliances that we might use every day? Your toaster example again.
Regulation 22 clarifies that electrically unsafe fittings include those with inadequate insulation, meaning the protective layers around live wires aren't sufficient, or those that are intended to have, or supplied as having, a safety function but completely fail to serve that function. Think of a safety cutoff switch that simply doesn't work. It's just useless. Similarly, Regulation 23 outlines electrically unsafe appliances, deeming them unsafe if they lack clear voltage marking, are not constructed safely under normal or even abnormal operating conditions, or if accessible unearthed conductive parts are separated from live parts by no more than basic insulation.
Basic insulation, meaning just one layer of protection.
Essentially, yes. It means a single point of failure could make the casing live. That's obviously very dangerous. This ensures that even individual components meet fundamental safety thresholds before they are put into use.
And what about residual current devices, or RCVs? They're crucial for safety, especially against electric shock, but can they also be deemed unsafe themselves?
Yes, RCDs, despite being safety devices, can themselves be deemed unsafe under Regulation 24 if they don't perform to strict standards. They need to work and work fast. For general use, an RCD is unsafe if its trip time is more than 0.5 seconds at its rated residual current, or more than 0.15 seconds when a fault current is 5 times its rated residual current. That's half a second and much less for bigger faults. It's also unsafe if its rated residual current exceeds 300 milliamperes, meaning it's not sensitive enough to detect smaller, potentially harmful leakage currents.
See, for medical locations, I remember you said those were stricter.
Much stricter. For RCDs in medical locations specifically designed to protect patients during treatment, the criteria are even tighter. An RCD is deemed unsafe if its rated residual current exceeds 10 milliamperes, a much lower threshold, or if it doesn't interrupt the current in all live conductors within a lightning-fast 40 milliseconds when passing its rated residual current, or 5 times that.
40 milliseconds, that's incredibly fast.
It has to be. These tight specifications reflect the critical role RCDs play in preventing severe electric shocks, particularly in sensitive environments where people are vulnerable, may be connected to medical equipment.
So when are fittings and appliances in use considered safe? Is there a common certification or tag that tells us they've been checked? You mentioned testing earlier.
Regulation 26 addresses when fittings and appliances in use are deemed safe. For fittings or appliances that are regularly hired, leased, or rented, think of power tools from a hire shop or perhaps appliances in a temporary office setup, they are deemed electrically safe if they have a current tag issued in accordance with ASNZS 3760.
ASNZS 3760, that's the test and tag standard, right?
That's the one. This standard details how to test and tag electrical equipment, particularly portable appliances and tools. If you've ever seen a construction worker's drill with a little colored tag on it, that's often a sign it's been tested to this standard, verifying its ongoing safety for use. This is especially important for hire and lease scenarios, providing clear, visible verification of ongoing safety. If we connect this to the bigger picture, these detailed deeming specifications significantly reduce ambiguity and provide clear, measurable benchmarks for compliance and enforcement. It's a proactive, preventative approach to safety.
Yeah, it avoids arguments about whether something might be unsafe. If it meets these conditions, it just is.
Exactly. It leaves very little to subjective interpretation, which is crucial when dealing with something as potentially hazardous as electricity.
That's a comprehensive overview of what's considered unsafe. Now let's move from individual components to the larger system, how electricity is supplied, from the power station all the way to your wall socket. These are the regulations governing the very backbone of our electricity supply.
Indeed. Regulation 27, Systems in General, establishes a fundamental requirement. Electrical installations operating at standard low voltage must connect to a MEN, multiple earth neutral system of supply.
The MNN system we talked about earlier.
That's right. This ensures robust earthing not just at the source, but throughout the network, which is critical for safety throughout the entire grid. It's the default standard here.
And what about voltage stability? Are there strict rules for how much it can fluctuate? Because that sounds like it could damage sensitive electronics if it's not well regulated. I know my computer doesn't like power dips.
Yes, Regulation 28, Voltage Supply to Installations, sets clear standards for voltage fluctuations. For installations operating at voltages other than the standard low voltage you find in most homes, the supply must be at an agreed voltage between the electricity retailer and the customer. And unless otherwise agreed, and except for very momentary fluctuations, this voltage must be maintained within a tight 6% of the agreed supply voltage.
Plus or minus 6%.
Okay, yes. This ensures consistent power delivery, which is vital for the safe and efficient operation of appliances and equipment, preventing damage and prolonging their lifespan. Similarly, Regulation 29, Frequency of Electricity Supplied, stipulates the standard frequency of 50 Hz, with permitted variations, ensuring system stability and compatibility for all connected devices.
That's a pretty tight tolerance, the 6%. And what about the overall safety and quality of the supply? What does that involve beyond just voltage and frequency?
Regulations 30 and 31 deal with safety and quality of supply, and these are crucial. They state that the electrical characteristics of the supply system, such as its impedance, which is essentially how much the system resists the flow of electricity, must not negatively affect electrical safety. Think of it like a plumbing system. If the pipes are too narrow or too wide in places, the water pressure becomes unstable. Similarly, if the electrical flow isn't just right, it can create risks or damage equipment.
So impedance needs to be within certain limits.
Correct. Furthermore, reasonable steps must be taken to limit maximum prospective fault currents to safe levels, preventing overwhelming surges that could cause significant damage, fire, or injury. The regulations also specify compliance with certain IEC standards for limiting interference from harmonics, like IEC 61032, and flicker, referencing standards such as IEC 61033.
Harmonics and flicker. Those sound like very technical issues. Is this something that could actually impact my appliances, or are we talking about highly specialized industrial settings here? Why are they so important for safety and quality?
That's a great question, and it absolutely can impact your daily life, even if you don't realize it. Harmonics are distortions of the pure electrical waveform, often caused by modern electronics like LED lights or computer power supplies. Excessive levels can lead to overheating in transformers and motors, interfere with communication systems, and even cause protective devices like RCDs to trip unnecessarily, which poses safety risks and disrupts supply.
Ah, so my RCD tripping might not be a fault in my house, but maybe dirty power coming in.
It's possible, though less common for domestic situations usually. Flicker, which is rapid changes in voltage that caused lights to visibly fluctuate, can be annoying and, more seriously, indicates underlying power quality issues that could impact equipment performance and longevity. By regulating these, the framework ensures a reliable, stable, and non-damaging power supply for everyone, from large factories right down to your home.
And what protects against those major fault currents you mentioned earlier, the ones that could cause significant damage, like a lightning strike nearby or a major short circuit?
Regulation 32, Protection Against Fault Currents, mandates that line function services, the companies that supply your power, must provide a service protective fitting, such as a circuit breaker or main fuse of appropriate rating. This fitting is designed to quickly interrupt the supply of electricity to an installation in the event of short circuits or earth faults on the mains. It's your installation's first line of defense against a catastrophic electrical event, preventing widespread damage or fire by isolating the problem area.
The big switch or fuse at the meter box, essentially.
That's usually where it is, yes.
And there's even a specific regulation for a particular type of system called SWARE systems in relation to telecommunications. That seems quite niche, but probably very important for those affected. SWARE, Single Wire Earth Return.
It is, and it's a great example of how detailed these regulations are to cover every potential hazard, even in specific geographical contexts. Regulation 33A covers SWARE systems and telecommunications. SWARE stands for Single Wire Earth Return, and these systems are typically used in remote, rural areas where it's not cost-effective to run 2 or 3 conductors over long distances. The regulation sets specific limits on the transverse noise voltage, that's the measured electrical interference across a telecommunication line, to no more than 0.5 millivolts. And induced voltage pushed onto the phone line by the power line to no more than 35 volts RMS impressed by the SWARE system on a telecommunication line during normal operation.
So it stops the power line interfering too much with the phone line.
Precisely. During any normal or fault-related operation, SWARE systems must also not cause earth potential rises coupled to the neutral conductor of a MEN system or voltages impressed on a telecommunication line that exceed the maximum voltages outlined in the I-22 directives. Those are international telecom standards. The why behind these regulations is multifaceted: ensuring system stability by controlling electrical interference, preventing damage to sensitive telecommunication equipment, and, crucially, protecting public health from electromagnetic interference that could disrupt critical communication or even cause direct harm. It's about maintaining a clear, safe, operational boundary between power and communication networks, particularly in challenging environments where they might run close together.
Fascinating how the regulations delve into such specific technical interactions. It really shows how interconnected everything is. Now, let's shift gears to what happens when new electrical systems are built or old ones are maintained. This is where the rigorous checks and balances truly come into play. We're talking about the journey from blueprint to reality and all the rigorous checks and balances required before a single electron is allowed to flow safely.
This is indeed the backbone of ensuring new electrical work is safe and that modifications don't compromise existing safety. Regulation 38, testing works before connecting to supply, is absolutely crucial. When prescribed electrical work has been done on any works, mandatory tests must be carried out before connecting new works to a power supply. The person doing the connection must be completely satisfied that these tests ensure the completed works are electrically safe, that the polarity and phase rotation of the supply are correct, that the protection of the supply is correctly rated, and that the works are fully compatible with the supply system. It's a comprehensive check.
Polarity and phase rotation. Getting those wrong could destroy equipment, couldn't it?
Absolutely, especially with 3-phase motors. For existing works following maintenance or alteration, similar tests are required to ensure the work hasn't reduced overall safety and any alterations are safe.
So it's not just about installing it, but verifying everything before it goes live. But what about ongoing checks once things are up and running? Does an owner just assume everything stays safe indefinitely?
No, that's not the case. Regulation 40, Safety Checks of Works, mandates that every owner of electrical works must establish and implement a system for regularly checking the electrical safety of those works. This proactive approach ensures that systems don't degrade into unsafe conditions over time through wear and tear or minor faults that might go unnoticed.
So owners have a duty for ongoing checks.
Yes. Beyond that, Regulation 41, Structural Loading on Works, addresses the physical integrity of overhead electric lines, requiring them to be constructed to withstand both static, their own weight and dynamic loading, like wind or ice, without damage or becoming unsafe. If structures are found incapable of supporting their design loads, strict deadlines apply for repair or replacement. Within 12 months generally, or more urgently, within 3 months if there's an immediate risk of injury to any person or damage to property other than the owners.
3 months if it looks like it might fall down soon.
Basically, yes. That's a critical safety net, especially for older infrastructure that might be deteriorating.
That sounds like a massive undertaking for large organizations that manage extensive electrical systems, like a power company or a large industrial site. What if they have their own robust safety system? Can they use that as an alternative compliance pathway instead of adhering to every single prescriptive rule in the book?
Yes, that's where audited safety management systems come in, covered by regulations 47 through 56. This isn't just another layer of bureaucracy. It's a sophisticated evolution of safety management for operators of electrical works. It acknowledges that for large, complex operations, a prescriptive rulebook isn't always enough to capture every nuance or the most efficient way to manage risk. Instead, it allows them to implement a comprehensive safety management system that complies with recognized standards like NZS 7901 or specific regulations 49 and 50, but under rigorous independent audit.
So it's a different way to achieve the same safety outcome.
Exactly. It's a shift from tell me exactly what to do to show me how you'll manage risk effectively, empowering industry with flexibility while demanding ultimate accountability for the safety outcomes.
So what are the key requirements for such a sophisticated system? What does it actually have to do?
The requirements are quite thorough. The system must provide for the systematic identification and assessment of existing and potential hazards, outlining clear steps to eliminate or minimize risks, and regularly assessing the effectiveness of those steps. It's a continuous improvement cycle. It also requires the thorough investigation of any accidents, a commitment to continuous enhancement of the system based on learning, and a scheduled audit program to ensure ongoing compliance and effectiveness. Importantly, the documentation of the safety management system, as per Regulation 50, must be fully documented and in a format that allows accredited auditors to read and understand it easily. Transparency is key.
And how are these systems verified? Who checks the checkers, so to speak?
Regulation 51 mandates regular audits by an independent, accredited auditor. The first audit must occur within 2 years of the regulation coming into force for that system, and then at least every 5 years. The auditor's role is to confirm that the system complies with the standards, that it is being actively implemented and maintained as written, and, most critically, that it effectively prevents any significant risk of serious harm or damage. They're checking if it works.
And if it passes the audit?
If the auditor is satisfied, they issue an audit certificate, valid for up to 5 years, under Regulation 52. Following this, the operator must make a statutory declaration to WorkSafe every 5 years, confirming their system has a current audit certificate, as per Regulation 53. This structured oversight ensures these alternative safety systems are just as robust, if not potentially more tailored and effective, than a purely prescriptive approach for complex operations.
Okay, so once the systems are built, and maybe an audited safety system is in place, how do we ensure the installations themselves meet the highest safety standards? Is there a process for certifying the designs before any physical work even begins, getting it right on paper first?
Yes, absolutely. Regulation 58 details certified designs for installations. A design for an installation or part of an installation is considered a certified design if it clearly identifies its location or proposed location and the specific standards with which it complies or is intended to comply. This upfront design certification is a crucial preventative step, ensuring that the safety measures are integrated into the blueprint before any physical construction or wiring even starts. It's about designing safety in, not trying to add it on later as an afterthought.
And what about the actual installation process? Are there specific standards they must meet based on the type of installation, like for a house versus a construction site or a hospital?
Absolutely. Regulations 59, 60, and 61 WA outline installation compliance standards, recognizing that different environments pose different risks and require different solutions. For standard low and extra low voltage domestic installations, which is most of our homes, they must comply with Part 2 of AS/NZS 3000, which is commonly known as the Australia-New Zealand Wiring Rules. This is the foundational document for safe domestic wiring.
AS/NZS 3000, the wiring rules.
Yes. Specialized installations have their own, often more stringent, specific standards. For electrical medical devices, it's AS/NZS 3003. For hazardous areas like chemical plants or petrol stations, it's the AS/NZS 6000 ZS39 series. And for construction and demolition sites with their temporary setups and harsh conditions, it's AS/NZS 3012. Installations in excavated areas, including mining or quarrying operations, must comply with AS/NZS 3007. This granular approach ensures that the unique risks of each environment are addressed by appropriate, highly specialized standards.
And what about something as seemingly simple as a wall socket? Are there specific rules for those, even down to the direction of the pins? Seems almost pedantic, but maybe it matters.
Even those are meticulously regulated for safety. Regulation 61A provides specific rules for 3-pin flat-pin socket outlets in low-voltage installations. If such a socket outlet, which complies with AS/NZS 3112, that's the standard socket we use, is installed, it must be wired so that it only receives standard low voltage. Crucially, the earth continuity conductor must be connected to the radial slot, the bottom one, and, most specifically, the order of connection in a clockwise direction when viewed from the front must be earth continuity, then active, then neutral.
Earth, active, neutral, clockwise.
Okay. Installing it incorrectly is an offense. This level of detail highlights how even the smallest components are regulated to ensure fundamental safety, because incorrect wiring, even for a socket, can lead to serious hazards like electric shock or fire if someone assumes it's wired correctly when it isn't. Consistency is key.
So once the work is done and those standards are followed, how is that all formally verified? What kind of testing is required before something gets connected and becomes part of our electrically powered world?
Regulation 63, Testing Prescribed Electrical Work, mandates that all prescribed electrical work must be rigorously tested before it's connected to ensure its electrical safety. This is a critical, hands-on final check. The only exception is for specific domestic wiring work where testing is not required to comply with Regulation 57, usually very minor things. Failure to test as required is an offense liable to a Level 2 penalty. This means that a competent person, usually a qualified electrician, must perform a series of checks, everything from insulation resistance to earth continuity, polarity, and earth fault loop impedance, to ensure the physical installation matches the certified design and is truly safe to energize.
So once the tests are done, then comes the paper trail, the certificates that verify the safety. This is where accountability really kicks in, isn't it? Creating a traceable history of the work.
Absolutely. The certificates of compliance covered by Regulations 65-69 are central to this. They are mandatory for both general and high-risk prescribed electrical work, though optional for low-risk work. A certificate of compliance must contain a clear statement confirming that the person issuing it is satisfied the work has been done lawfully and safely, and that the information in the certificate is correct. It's a formal declaration. It must also include an authentication mark, as specified in Regulation 111B, which is a unique identifier confirming its legitimacy. Crucially, it needs to have a copy of any manufacturer's instructions, supplier declarations of conformity, and certified designs that were used for the work, either attached to it or clearly referenced electronically if impractical to attach. It links everything together.
So it's not just a tick box, it's a detailed, verifiable record of compliance. What defines lawfully and safely in this context for the certificate?
For a certificate of compliance, lawfully and safely means that the work has been performed in full accordance with these regulations, that all necessary testing has been satisfactorily completed, that the installation is electrically safe as a result of the work, and that the work has not adversely affected the safety of any other part of the existing installation or its fittings. There are also clear offenses for noncompliance, such as issuing a certificate that doesn't meet content requirements or contains incorrect information, or if the person issuing it isn't authorized to certify that specific type of work. This ensures integrity and accuracy throughout the certification process.
Beyond the work itself, there's also an electrical safety certification for the overall installation. That sounds like a slightly different focus. How does that differ from the certificate of compliance?
Yes, that's a crucial distinction, covered by Regulations 74A to 74D, which outlines electrical safety certification. This certificate is issued after the prescribed electrical work is complete and the installation, or part thereof, is connected or reconnected to the supply. Its distinct purpose is to certify that the installation itself is safe to use based on the grounds that it is electrically safe and fully complies with the regulations as a whole. If the work was maintenance or an alteration, it also confirms that the work hasn't adversely affected any other part of the installation. So, to clarify,
Yeah, please do.
the certificate of compliance is about the specific work done by the electrician being safe and lawful. The electrical safety certificate is about the overall state of the installation after that work, confirming it's safe to energize and use. One focuses on the task, the other on the system's readiness.
Got it. Task versus system readiness. And what happens to all these crucial certificates? Is there a strict record-keeping requirement, like a digital paper trail? They must be kept somewhere, surely.
Absolutely. Record keeping is covered by Regulations 74E to 74H, and it's vital for accountability and traceability. Copies of both certificates of compliance and electrical safety certificates must be retained for at least 7 years. This long retention period is crucial for identifying historical work, troubleshooting future issues, and for regulatory oversight.
7 years, huh?
They must also be readily provided to WorkSafe, the Electrical Workers Registration Board, the registrar, the territorial authority, the contractor, or the owner-occupier within 10 working days upon request, so they need to be accessible. For high-risk work, specific details of the work and its certificate of compliance must also be lodged on a central database within 20 working days of the inspection. This creates a national record for the most critical jobs.
How do they track the physical location of these installations, especially those that might be temporary or mobile, like a food truck or a caravan? You can't always use a street address.
Regulation 74I, Location of Installations, specifies how different types of installations are identified. Fixed installations, like your house, are identified by a street address or GPS coordinates. Pretty standard. Connectable installations, such as caravans, relocatable buildings, or pleasure vessels, use a unique identifier, like a chassis number or hull number. For installations that will be in a permanent location but aren't yet, like a prefabricated building section, a unique identifier is fixed to the item itself. This rigorous documentation ensures accountability and a traceable history of electrical work, which is absolutely critical for long-term safety, maintenance, and emergency response. It creates a robust audit trail for every piece of electrical work, making it easier to identify and address issues over time, no matter where the installation may be.
Beyond the initial certification, are there ongoing checks required for specific types of installations, like those in caravan parks or medical facilities, which might have different risk profiles or heavier use?
Yes, periodic assessments are mandated under Regulation 75 for certain installations precisely because of their unique risks or usage patterns. It's not just a one-off check for these places. For example, low-voltage installations in caravan parks, where many different people connect their portable homes, must be assessed in accordance with ASNCS 3001 at intervals not exceeding 5 years. Similarly, boat marinas must follow ASNCS 3004.1 every 5 years. Lots of exposure to weather and water there.
Makes sense.
Installations at construction and demolition sites, covered by ASNCS 3012, require ongoing, often more frequent assessments due to the dynamic and hazardous nature of those environments. Things change fast on a building site. Carnivals and fairgrounds with their temporary high-traffic setups require annual assessments under ASNCS 3002. Hazardous areas and medical locations, due to the heightened risks involved, like the vulnerability of patients or the presence of flammable materials, also have specific, often much more frequent, assessment requirements following standards like ASNCS 6007 9.17 and ASNCS 3003, with medical locations requiring checks every 3 years.
Those are all environments with very specific or transient electrical use, where regular checks are clearly vital.
And what about connectable installations, like caravans or mobile homes themselves? Do they need a periodic check, like a car's warrant of fitness?
Absolutely, and it's a critical point for anyone who owns or uses one. Regulations 76 through 78 deal specifically with connectable installations and the concept of a warrant of electrical fitness. This warrant is mandatory for vehicles, relocatable buildings, or pleasure vessels that connect to an external power supply. It's essentially their electrical warrant of fitness, or EWOF.
EWOF, right? I've seen those stickers. Yes. No external supply can be provided to these installations without a current warrant of electrical fitness, which must be issued by an authorized person after an inspection. This regulation addresses the unique risks associated with transient, outdoor, or sensitive electrical environments, ensuring that even temporary structures that move between locations maintain a consistent baseline of electrical safety. It's akin to a vehicle's warrant of fitness, but for its electrical system, ensuring it's safe to plug into the grid wherever it goes, protecting not just the owner, but anyone else connected to the same supply at, say, a campground.
So we've talked about large-scale installations, individual works, and mobile setups. But what about the products we buy and use every day in our homes and workplaces? The appliances, the fittings, how are these regulated for safety before they even reach us on the store shelf? It seems like a massive undertaking to ensure everything from a hairdryer to a microwave is safe.
It is indeed a massive undertaking, and it's a critical layer of protection that many people aren't even aware of, operating mostly behind the scenes. Regulation 80, new and used fittings and appliances to be electrically safe, sets the fundamental requirement. Every new or used fitting and appliance sold or supplied in New Zealand must be electrically safe. Full stop. For new items, they are deemed safe if they comply with ASNZS 3820, which is the general safety standard for electrical equipment, or an applicable official standard listed in Schedule 4, or if they fall under the Conformity Cooperation Agreement for certain imported appliances, particularly from China. This provides clear benchmarks for manufacturers and importers, putting the onus on them to ensure safety at the source before it even gets here.
And what about used appliances? How are they verified as safe for resale, given they might have wear and tear or maybe dodgy repairs in the past?
For used appliances, the criteria are slightly different but still rigorous. They are deemed electrically safe if, at the time they are sold or offered for sale, they have been properly tested, inspected, and tagged in accordance with ASNCS 5761.
Another test and tag standard.
Yes, this one is specifically for the safety of in-service appliances, including those being resold. Alternatively, if a used appliance is not safe for use, it can be deemed safe for sale only if it has been adequately disabled and marked according to AS/NZS 4701, clearly indicating it is unsafe or for parts only.
So you can sell it for scrap, but not for use,
Yeah.
unless it's tagged safe.
Correct. Used electrical medical devices, given their critical function and the vulnerability of patients, have even stricter requirements, mandating specific testing and marking by qualified professionals before resale.
And is there a formal declaration required from suppliers? Even for common household items, does the importer of, say, a kitchen mixer have to declare it safe?
Yes, for what are called declared medium risk articles, Regulation 83 requires a supplier declaration of conformity, or SDOC. WorkSafe can gazette certain low voltage or extra low voltage fittings or appliances as medium risk, which means they fall into a category where a formal declaration is needed from the NZ supplier. Before these articles can be sold, the New Zealand manufacturer or importer must have made a supplier declaration of conformity. This declaration must clearly describe the article and formally state its compliance with AS/NZS 3820, applicable or Schedule 4 standards, or the Conformity Cooperation Agreement. This puts the direct onus on the supplier to formally declare their product's safety and compliance with the regulations. They have to stand behind it.
So medium risk needs a declaration, an SDOC. What about high-risk articles? Do they need direct approval from WorkSafe before they can even be sold? Sounds even stricter.
Correct. For declared high-risk articles, which WorkSafe also specifically gazettes based on potential hazards, direct approval by WorkSafe is required, as outlined in Regulation 84 and 85. Any person wishing to sell such an item must apply to WorkSafe for this approval, which may involve referral to an experienced independent person for advice on compliance. WorkSafe then notifies the applicant of its decision and any conditions of approval. This tiered system, deemed compliance for low risk, declarations for medium risk, and direct approvals for high risk, coupled with mandatory testing after certain work, provides robust layers of protection.
Testing appliances after certain work, you mentioned that. What does that involve in practice for, say, a repair shop fixing my washing machine?
Regulation 90, testing appliances after certain work done on them, is key here. It mandates that a person must test an appliance for electrical safety before releasing it from their control if they have performed any prescribed electrical work on it or any work that might reasonably affect its electrical safety. The testing must confirm it's electrically safe, referencing specific standards like ECP 50 for domestic appliance maintenance, AS/NZS 3551 for medical devices, or AS/NZS 5762 for testing other low or extra low voltage appliances after repair.
So the repair has to test it before giving it back.
Yes. If the appliance is found to be electrically unsafe after the work, it must be adequately disabled and marked, often in accordance with AS/NZS 4701, to prevent its further use until it is made safe. This system of declarations, approvals, and post-work testing ensures that products on the market, whether new or used and after any repair, meet fundamental safety benchmarks, significantly impacting the safety of everyday electrical convenience for you, the listener. It's a comprehensive approach to product safety from cradle to grave, really.
Now, let's take a deep dive into an area with some of the most unique and heightened electrical challenges: mining operations. The risks here are very different from a domestic installation, with potentially explosive atmospheres, confined spaces, water, dust, heavy machinery. The regulations must reflect that intensity.
You're absolutely right. Mining environments present unique and potentially catastrophic electrical hazards, and the regulations are specifically tailored to address them. It's a whole different ballgame. Regulation 78B covers obligations in alluvial mining and quarrying operations, requiring operators to ensure compliance with Schedule 8 for all mobile and relocatable mining electrical equipment. This schedule contains incredibly detailed rules for these specific, often harsh, and inherently dangerous environments.
What kind of standards do the equipment and conductors in these operations have to meet? I imagine they're far more robust than your average household wiring, built like tanks.
They absolutely are. Regulation 78C specifies standards for equipment at alluvial mining and quarrying operations. All mobile and relocatable mining electrical equipment and the conductor supplying it must be designed, constructed, tested, inspected, and connected in compliance with applicable official standards listed in Schedule 4, and specifically with AS/NZS 3007, which is the specialized standard for electrical equipment in mines and quarries for surface installations and associated processing plant. This means equipment is designed to withstand extreme conditions, including dust, moisture, vibration, and potential mechanical damage. Robust is an understatement.
And like other installations, are there periodic safety assessments for mining equipment? because with constant heavy use and harsh conditions, things must degrade quickly or get damaged.
Yes, and they are critical, forming a continuous cycle of safety verification. Regulation 78K outlines periodic safety assessment programs. Operators must have programs for regularly assessing the electrical safety of mobile and relocatable mining electrical equipment. This includes verifying compliance with general safety duties and rigorously assessing for electrical safety and compliance with Schedule 8. For underground coal mining, a key focus is on ensuring robust controls are in place to prevent the ignition of flammable gas methane, usually which is a constant and deadly threat.
Ignition prevention is paramount there.
Absolutely. These assessments must be carried out in accordance with specific standards like BS 6164 for tunneling operations or the equipment's certified design for underground operations. This emphasizes the heightened risks in mining environments and how these specific regulations are meticulously tailored to mitigate those unique dangers, considering everything from explosive atmospheres to confined spaces and heavy-moving machinery.
Let's get even more specific for underground mining. What are some of the granular rules outlined in Schedule 8, Part 3 and 4 for these operations? It must be incredibly detailed.
Schedule 8, Part 3 and 4 delves into the essential detail for underground mining safety. Clause 17, consistency with certified design, mandates that all mining electrical equipment and conductors must be installed, tested, inspected, and connected strictly in accordance with the certified design for the mining operation. This ensures that the actual installation matches the rigorously approved plan, preventing dangerous deviations or unapproved modifications deep underground. Clause 18, installation of fixed equipment, requires that fixed electrical equipment be installed in protected places, preventing overheating, mechanical damage, or interference from things like falling rock or water ingress.
Are there specific mandatory warning notices required given the extreme dangers of a mine? More than just the usual signs.
Crucially, yes. Clause 4, permanent notices, requires durable, permanent notices to be conspicuously affixed near every place where mining electrical equipment is installed in an alluvial mining, or quarrying operation. These notices must prohibit unauthorized access or interference, except for emergency isolation. They also must provide clear, concise advice on what to do in the event of a fire or electric shock. For underground mining operations, additional notices are required at the entrance and near communication devices, providing advice on how to isolate the surface electricity supply to the underground parts of the operation. That's vital information in an emergency.
Knowing how to cut the power from the surface.
Yeah, this ensures critical, life-saving information is always accessible, even in low visibility or high-stress situations underground.
And what about record keeping for equipment in such a complex, vast environment? Is it simply enough to know it's there somewhere? How do they keep track?
No, it's far more detailed than that. Clause 5, keeping records and plans, obligates operators to maintain comprehensive records and plans of all mining electrical equipment and conductors. This enables them to readily locate every single piece of equipment at the operation, which is vital for maintenance, inspection, and particularly for emergency response in complex underground networks. You need to know exactly where that cable runs. Furthermore, specific technical standards are outlined for cables. Clause 26, cable standards, requires reeling or trailing cables, those that move with machinery like shuttle cars or drills, to comply with ASNZS 1802, and all other cables used underground must comply with ASNZS 1972, ensuring their exceptional robustness and resistance to damage in harsh mining conditions. These are seriously heavy-duty cables.
And what about variable speed drives, which are common in heavy machinery and mining? Are there specialized rules for those? They involve complex electronics?
Yes. Clause 29, variable speed drives, dictates that these must be specifically designed for use in underground coal mining operations, which often have that risk of explosive gases. Standard industrial drives may not be suitable. The manufacturer's instructions for these specialized drives must be kept and meticulously followed for installation, emphasizing the absolute need for specialized, certified equipment and strict adherence to its specific safety protocols in such high-risk settings. The sheer gravity of these environments means that every component, every procedure, and every piece of information is subject to the most stringent safety requirements, all tailored to mitigate potentially catastrophic dangers. This is a prime example of how regulations adapt to highly specialized and dangerous contexts, proving that electrical safety is far from a one-size-fits-all approach.
Finally, let's explore the practical, human elements of working with electricity and the overarching mechanisms for ensuring compliance. It's about the people on the ground doing the work, their employers, and WorkSafe's authority to keep things in line. The enforcement side.
Indeed. Regulation 100, Safety Responsibilities of Person Who Carries Out Work, states the fundamental duty of any person performing electrical work to ensure safety while doing so. This means actively assessing and mitigating risks in their immediate work environment. Personal responsibility. Expanding on this, Regulation 101, Responsibility of Employers for Safety of Employees, mandates that employers ensure their employees are suitably qualified, adequately supervised, and have all necessary equipment and training to perform their work safely. This highlights a crucial layered approach to responsibility, from the individual worker carrying out the task to the employing entity providing the framework and resources for safety.
What about working on live power lines? That sounds incredibly dangerous and like it should be strictly prohibited unless absolutely unavoidable.
It is, and it's heavily restricted for precisely that reason. Regulation 102, Work on Live High-Voltage Overhead Electric Lines, prohibits such work unless very specific necessary equipment, like insulated tools, booms, protective gear, is used to ensure safety, and only if other robust safety procedures are rigorously followed. It's specialized work for highly trained crews. Similarly, Regulation 103A imposes strict conditions for work on or near bare live conductors in alluvial mining operations, and quarrying operations. Such work is only permitted if isolation is genuinely unreasonable, which is rare. It's demonstrably reasonable under all circumstances to work near live conductors, and all suitable precautions, including robust protective equipment and procedures, are taken. De-energizing is always the preferred option.
So live work is the absolute exception, not the rule.
Definitely. These rules translate directly into stringent, life-saving, on-the-ground safety procedures for electricians and other workers, emphasizing isolation first and protective measures as the absolute last resort when de-energizing isn't possible.
And if high-voltage fittings are isolated, do they still need to be earthed before work begins? I'd imagine even an isolated line could pose a risk from induced voltage or accidental re-energization.
You're right to be cautious. Yes, Regulation 104, Work on Isolated High-Voltage Fittings, generally requires such fittings to be earthed before work commences and to remain earthed until the work is completed. This applies even if they are disconnected from the power source, given the significant residual risk of serious harm if they accidentally become live again or hold a dangerous capacitive charge. Earthing provides a safe path. There are exceptions if approved employer procedures and appropriate equipment, like testing devices, are used, but the core principle is maximum protection from accidental energization through earthing.
What about stringing new conductors where existing ones are already in place? Like adding a new line to existing poles. That sounds like a complex dance to avoid contact.
It is, and it's carefully regulated. Regulation 105, Work Stringing Additional Conductors, requires that either the existing conductors are isolated and earthed before new work begins, or the additional conductors themselves are earthed during the stringing process, and appropriate associated equipment is used to maintain safety clearances and control. This prevents dangerous cross-energization and ensures that workers are protected from live parts they might inadvertently contact. And importantly, Regulation 106 notices when working on works and installations mandates clear warning notices, like danger, men working online, at points where a power supply may be connected or restored if works are isolated and there's a risk of unintentional re-enlivening.
And using locks.
Yes. If a locking facility exists for isolation, like on a switch or circuit breaker, it must be used. Lockout-tagout procedures are essential. These are practical, everyday procedures designed to prevent catastrophic errors in the field due to oversight or accidental reconnection by someone else.
So we have these detailed regulations and responsibilities, but who has the overarching authority to ensure compliance, grant exemptions, and react when things go wrong? Who's the regulator?
That overarching authority lies with WorkSafe New Zealand, the primary regulator for workplace health and safety, which includes electrical safety. Regulation 108 grants WorkSafe's power to prescribe forms, allowing them to create necessary forms for compliance and reporting, standardizing the paperwork. Critically, WorkSafe also has power to exempt from requirements under Regulation 109, meaning they can grant specific exemptions from certain regulations under specific controlled conditions.
Why would they grant exemptions?
This provides necessary flexibility where strict adherence might be genuinely impractical or technically impossible, but safety can still be assured through alternative, demonstrably equally effective means. It's not a free pass. It requires justification.
And in truly urgent situations, can WorkSafe issue immediate directives without going through a long bureaucratic process if they see something really dangerous?
Absolutely. Regulation 110 details WorkSafe's power to issue urgent instructions, orders, or requirements. These are direct directives that can be issued for immediate safety concerns, for instance, if a significant and unmanaged hazard is discovered during an inspection. These urgent orders remain in force for up to 6 months, allowing WorkSafe to respond swiftly to new or escalating dangers and demand immediate remediation actions. Furthermore, the regulations address what happens when an accident does occur. Regulation 112 details that must be provided in reports of accidents. These reports must include specific, comprehensive information such as contact details, the precise date and time, a complete description of the accident, details of any injuries or damage, witness information, possible causative factors, and any resuscitation applied. This ensures thorough investigation and crucial learning from incidents, contributing to continuous improvement in safety protocols and preventing recurrences.
And is there a clear enforcement mechanism for noncompliance? Because regulations without enforcement are just suggestions, aren't they? What are the consequences?
Yes, very much so. Schedule 3 of the regulations details infringement notices, outlining the process for fines and fees for specific breaches, similar to a traffic ticket for less serious offenses. It also outlines the option to request a hearing if you wish to dispute it. For more serious breaches, prosecution under the overarching Health and Safety at Work Act is possible. This underscores the robust enforcement mechanisms in place for noncompliance, ensuring that the regulations have teeth and that breaches are addressed appropriately depending on severity. There are also provisions like Regulation 111A for the consolidation of certificates, allowing multiple electrical safety certificates, or certificates of compliance, to be combined into a single document, which streamlines administration, especially for large projects. And Regulation 111B requires an authentication mark on certificates, often linked to the registered electrician's details, further enhancing security and traceability. All of these elements, the detailed rules, the responsibilities, the checks, the reporting, and the enforcement combine to ensure comprehensive safety in the electrical industry, from the smallest appliance to the largest power system, and ensures that when things go wrong, there's a clear process for accountability and learning.
As we bring this deep dive to a close, it's abundantly clear that the Electricity Safety Regulations 2010 are far more than just a dry legal document. They truly are an invisible shield, meticulously defining, enforcing, and maintaining electrical safety across every facet of our lives, from the smallest home appliance to large-scale supply systems and even complex high-risk mining operations. The scope is immense.
So, what does this all mean for you, the listener? It means that these detailed rules, all these regulations we've unpacked, are not just bureaucratic hurdles. They represent a dynamic, evolving system, constantly adapting to new technologies, unforeseen risks, and the complexities of human interaction with electricity. They are designed, above all, to protect lives and property, creating a profound and unseen safety net that we rely on every day. This deep dive should hopefully give you a new appreciation for the unseen work, the constant vigilance, the layers of testing and certification, and the intricate web of standards and responsibilities that go into keeping your world safely powered. Knowing the depth of these regulations and the constant vigilance required across so many diverse environments, how might your perception of everyday electrical convenience change? And perhaps, what new questions does this raise for you about the future of electrical innovation? Think EVs, smart homes, renewable energy, and the ongoing challenge of maintaining safety in an increasingly electrified world. It's a constant evolution.